So I'll share my screen. And we will start from where we left off. Okay, so the plan now is, we have seen basics of OpenMP. I'll quickly show how to use some more OpenMP concepts. Then we'll parallelize our thermal code also. And then we'll quickly move to MPI. So I'm on the login node where we were benchmarking the copy code that we have. So, are there any questions about this simple copy code or the OpenMP, this Pragma OMP parallel for this part? There is, just let me know now, because now I'm going to go at a little faster speed. Huh?
Hey, Samidi.
Yeah.
So, you are, before stopping the clock, you are printing something, a reference value equal to something.
Yes.
So, I think if you remove that and put it after that, it will slightly increase the speed of the code, no? Increase the...
That is done for time.
This one. Okay. Yeah. That will be hardly 1 millisecond, but okay. Yeah, you're correct. In general, you're correct. Yeah. Oh, sorry. Yes, you are absolutely right. Okay.
No, I just wanted to check how much difference does it make.
Oh, it will be hardly 1 millisecond. Okay. Because it's just one line, no? So one printed terminal. So it won't be that much. If it was a big file you're printing, yes, then it makes sense. So 330, 947.
Earlier it was 340 something, no?
This is fluctuation. Like I can run it again, it will change. Oh, sorry, wait. Let me just get rid of this big thing. Export OMP display env is false. It's just fluctuation.
Okay.
That will be a few milliseconds at one time. I mean, if it was a big file, yes, it would have made a big difference, yes. But in general, yes, it's good. It's good to print out after the timing loop. Yeah. So, fine. Any other questions regarding this code? No questions. Okay, fine. So, now a small thing that we can try out is, let's see. We won't go into compute bound kernels in this course, because compute bound would, as you saw, that was a compute bound kernel which we are doing in crypto. You can run it and try to parallelize it across for loops also and so on, and you can see the scaling numbers, how long it is taking and how the number is reducing with number of cores instead of memory channels and all. So basically, ideally, you should be able to scale 128 times. It won't be exactly that. You'll be able to scale 100 or 50, 60, 70 times at least. I don't have to check. Okay, so something like that. So now, regarding this parallelization, this was an example of a very simple for loop which you parallelized. Now, suppose there are dependencies that, suppose I have to multiply by a number here, by a scalar number. And the scalar number is basically the sum of all the values which were updated in the previous step. So suppose the scalar number comes from, this won't be a good enough example. Okay, fine, let's leave this one now. I was going to do OMP sync threads and all those things, but let's just leave it at this. If you want to do summation, so suppose you're doing this copy operation. Now you just want to gather all the sum over the A array. So basically something like this. So again, int x equals 0, x, nx. And you want to do a sum like my double sum 0 and x. How would you parallelize this? Because if this array is large, is there a way we can parallelize? So you can do that using OpenMP itself, using a pragma. You can put a hash pragma OMP parallel for. But the thing is now, this sum value, which you're trying to gather everything into, that is defined as a global variable. Okay, which means all the threads that you spawn will try to add or increment this sum variable. Essentially, what will end up happening is, suppose there are, so let's go to the slide which we were using previously and remove this. So there are multiple threads which will come in, which are trying to write to the same variable. And you have this sum. You have this sum variable. And this thread, suppose, wants to increment a value of plus whatever value it saw. So let me call this, I want to add plus equals 1. Okay, sorry. Okay, this thread wants to add plus equals 1. The other thread now wants to add plus equals sum of 5 and so on. So the question is, if the sum value initially, before these threads were trying to write something, if it was suppose it was 4 here, the value of sum, and now these all threads are trying to write to the same thing, what do you think will be the value here? Sum. See, there the CPU doesn't have any preference of that this thread is more important than this or this and this. Okay, so when this thread is going to write the same thing, it completely depends on whichever thread comes first. Okay, so now if this thread came first and wrote to this sum variable, then this sum value will now become 4 plus 1, which is 5. And now if this thread, so this writing operation plus equals 1 can be seen in a much more broken down step, where it essentially does what? It reads the value of sum, increments it by 1 in a register, and then writes the register back into the RAM memory. Now, when this thread is doing the first part, so basically when it is doing this portion, so there are 2 steps to this. So from the sum variable, read it to some register EAX, and then the second operation is EAX incremented with 1 is equal to, let's write it down properly. It will be much easier to understand. The operations are this. These are the internal operations which are going on. Or if you really look at the code, it will be that move thing from sum to EAX. So let's move sum to EAX. That is the first instruction that will get generated. Then you'll have add EAX with the 1, where 1 is stored in some other constant. Okay, so suppose this is ESC, and you did a move of ESC like this. This thing, and this will get stored in EX, and then you'll be moving whatever is in EX to some like pointer or pointer to some, basically. Okay. So this is how it, these are the steps. Now, when this thread has read this PTR sum value, let's do big, let's remove PTR. When you have read sum to EX, it is possible that this thread came and tried to also read the sum value. So essentially, this thread here will end up reading sum equals 4. Then it will be plus 1, which is, then it will become sum equals 5, or it will write back sum equals 5. But if the same thing was being done simultaneously by this guy, then this plus 3 guy would have ended up writing what? So let me just overwrite this one. This one would also read 4, and then it will try to increment by plus 3. So this will become 3 plus 3, then it will put 7, and then it will try to write back 7. Okay. Which is wrong, because ideally, if we were trying to add up plus 1 and plus 3, we should have gotten 4 plus 3 plus 1, which is 8. But here, either we will get 5 or 7, depending on who writes back first. So this is called a race condition, where two threads are trying to simultaneously update the same value, and then it ends up doing a incomplete calculation, or uses the stale value to get a intermediate value and weird values and so on. Okay? So we ideally should always avoid these kind of things. So what we usually do is, whenever we want to do this kind of a collection operation inside a parallel region, you always mark those regions as serial. You have to, one way of doing it is just to mark those regions as serial. The way inside a parallel region you mark something as serial in OpenMP is hash pragma OMP critical. Okay. So any region of encompassed by these brackets surrounding OMP critical will be done serially. So at this, when OpenMP encounters this part, all the threads will wait in line, and whichever thread came first, it will be queued up. It's basically a queue which will come in. Slowly, one by one, they'll update to some their values and then go out. Then after they go out of this, again, if there were more codes like this here, the other codes here, then it will again do it parallelly, and so on. So these are critical regions, but effectively then your whole thing becomes serial here. Then what's the point of using OpenMP and so on? So instead of going full serial here, OpenMP gives you something like reduction clauses, so which allow you to reduce or do a gather or this kind of accumulation of values across huge arrays into a single value, without having to use this fully serial thing, or without to even face race conditions. This intermediate way is done in a very hierarchical way as a tree. Like basically what happens is, OpenMP will, out of suppose 10 threads, OpenMP will say out of 10 threads, every two thread reports to one thread. Okay, it will create a hierarchy. So basically then two threads will keep doing a local accumulation of their own, and then just send that locally accumulated partial sum to their reporter manager thread, and then that manager thread will sum up those two values and then pass it on to its manager and so on till you get to a single thing. So basically, if you had to write it down yourself, how it would look like is, you would essentially, for doing this sum, you would end up creating something called a temporary array called a partial sum. Okay. Partial sum equals new double. Whatever the number of threads is. For OpenMP, you can get the number of threads in a serial region. We're outside this OpenMP parallel fork, so it's a serial region here. OMP get max threads. If you're inside a parallel region, you can get the number of threads with OMP get num threads. Okay. This is a serial region, and since I'm creating it, let me quickly free it up also after I'm delete partial sum. So what in the parallel region, what you'll do is you will identify. So forget about this OMP critical. The nicer way of writing or the faster way of writing is okay, fine. Let's just time this once. Huh? We will quickly time this once before actually doing the sum. So essentially, we expect this to be serialized. And again, if we don't print out the value, compiler will try to play smart and say, "Key, they don't need the value, optimize the loop away," and then horrible things will happen. So we will just print the sum. It's this one, and then we'll see how much the time is. So this is going to be again. Can someone tell me how many operations are going to be? Is this a compute bound thing? Is it a memory bound kernel? This part. Imagine the critical is not there. So otherwise also, is it compute bound or because there's a plus operation here? Okay, off. Huh?
So one addition, I think one read. So some it read, no? So two reads, one write, one listen.
Yeah. So the thing is, usually if you have a single number like this, and if there are not too many free variables around being used continuously, most probably the something will be in cache. Huh? Anyway,
Oh,
so this and this, these two will anyway be in cache. There will be only one read and one
yeah.
addition. So now it depends on your processor clock cycle frequency and your uh, RAM clock cycle, which is the higher and lower. That will determine like whether one read is slower than one plus addition or one read is faster than one addition, and so on. So let's do a check, like let's run it and see. So that's why if it is actually a one read, if this is, see, usually as I was saying yesterday, currently the status of the computing industry is such that the flops are so high, most codes can't even saturate the huge amount of flops that a processor gives opportunity for. So on the other hand, RAM speeds are very low comparatively. So that's why most codes are nowadays memory bound. When HBM comes and so on, then we can see. Except for the crypto codes. Crypto codes are usually always compute bound. So if there was only one read, then we would have to, in our this calculation of effective bandwidth that we're getting, no, the theoretical estimate, then there will be one read, one write for this kernel for 1 billion elements. Again, for this 1 billion thing, we are doing it serially. So we will have to add up 1 billion into one read. So the number of operations will be 3 here. Actually, it will be a bit more than 3 because it is happening serially, not parallelly. So it won't utilize all the RAM memory bandwidth parallelly. It will be serial there. So okay, anyway, let's see. Serialized, how much elapsed time is taken. Forget about the bandwidth calculation now. That will be wrong a bit. So what happened? No? What is the thing? Oh, acha, acha. I defined it inside the samples loop. Okay, fine. We'll define it outside. Overall samples also. So we will do it with 16 threads. That's supposed to give the best number. So we'll do it with that. Huh? And those are anyway exported, the other factors. And let's do. We'll just look at the time taken. This will be bad because it's serial. That plus part is serial. OpenMP will be like, you asked me to spawn so many threads and then you're doing serial. What is the point of calling it that? As you can see, it's taking quite a bit of time. Should we just decrease the size a bit? Okay, let's decrease the size a bit. So let's see if it's even running or not. Wasn't only. Okay, fine. We'll make 1 million. 1, 2, 3. 1 million. You can become so. How much will it be? 7 seconds. 5 seconds. Okay. So we'll do it with 1 million, huh? And try to speed this up. So as you can see, what we're trying to do is, this will anyway go on in parallel. Here we are essentially doing this some serially. So calling OMP parallel for and then calling OMP critical essentially basically removes these two. It nullifies each other, right? So this is a pure serial part. So we'll just quickly write again just to make it uniform. 7 seconds we are getting. Okay, 5 seconds, 5.6 seconds. So bandwidth calculation, you leave it because it's anyway wrong. And the reference value for sum is 2.5 and 10 to the power 7, which is correct because we have used 10 to the power 6 here, and we are multiplying the sum of A everywhere is going to be equal to B, which is 2.5. So 2.5 into 1 million elements into 10 iterations. So it's 2.5 into 10 to the power 7, which is correct. Now we are going to do a parallel sum, which will essentially try to reduce the serialness of this critical business. If there are situations where you have to serialize it, nothing to do, you have to use OMP critical. But if you have simple gather operations like this, you can do OMP. Okay, you can do it forgotten the syntax for this. I haven't used it in 7 years. Or is it reduction class? Quickly check. Where is it? Like simple. Hash. What a simple example. Or say OMP critical, reduction. Here. So what you say is, this was your initial thing that you were trying to parallelize. You'll say OMP parallel for reduction, and then what is the type of reduction that you're trying to do? Okay, what is the operation? Here you're trying to just sum. So you'll call it sum or plus, and into which variable are you trying to sum all these things into? So sum. So essentially it will know that this sum variable is going to be treated very specially. It's actually something where all threads are going to write to. So that's why you have to say, and what is the operation? So here you can put subtract, which means sum. So if you have operations like this, then you'll write minus there. Or if it is multiply, all of them, then it will be multiply in there also, and so on. So that is the operation that you do. Or if you are trying to take the minimum of everything. So basically instead of this, which was basically this thing, if we are trying to find the minimum of all the elements in the array, we would have written a code like this. Then basically that would mean. So whatever function you're calling, the binary function you're calling on these two elements, you pass it there. Okay. So we'll try to do at something only. And we will try to see how much time it takes. Okay. As you can see, it summed up very fast. Sum is correct. It's not like it ignored that portion. So you can see how much your serial code was trying to take with 1 million sums. And this is the parallel thing. Now, as you can see, the bandwidth number has come to half then of 340 that we were trying to get. That is because we are trying to do this read also here. There's an extra read going on here. And plus it also depends a bit on how it is implemented internally. So when you have things like this, it would be better to get the theoretical estimate by seeing what the serial version would look like. As I was saying, there will be one read here. So that means for each variable, like each of the elements, you'll have one read. So this will be 3. If you put that 3 here back, you can sort of find out how efficient MPI's implementation of this sum business is. 281, which is okay, because as I was saying, internally MPI will try to do a hierarchical thing in the sense that if you wanted to look at the basic schematics of how it will do it, is you will have an array of values like this. Suppose this is x, a of 0, a of 1, a of 2, and so on. And what will ask the n number of threads to do is, suppose this is handled by thread 1, suppose this is handled by thread 2, and suppose this chunk of the array is handled by thread 3. What MPI will ask, wait, let me put one more, that way I can draw two hierarchies. Sorry, a bit. So what MPI will, not MPI, sorry, OpenMP will ask these threads to do is, so thread 1 here, this is in charge of this portion of the array when it's doing that OMP parallel for. This one is in charge of that, and so on. Internally, MPI will say that, okay, I'll create a temporary variable, which is here. this is a partial sum. So part or P1, P01, because thread 0 will do a sum here of its own thing. So thread 0 will do a sum P0 of all these for whatever array size chunk it is responsible for. Then P1 will do a thread 1 will do a partial sum in P1 of only its chunk, and so on. Then these two will be added to this. Similarly, for the other threads, we will have something like this and something like this. P2 and 3. And similarly, 2 and 3 will add up to some partial value 2, 3. And then once these are filled up by all the threads, then one thread will come and fill up this value, which is 0, 1, 2, 3. Like this, it will keep on doing a hierarchical binning of all the individual sums like this. So then, depending on how big the array is and how many threads are handling it, you will trunk it at some levels, 5, 6 levels above, and that final sum will be stored in this sum variable. This is how the breakup happens internally. So all this complication is done away, means you don't have to suffer through that. Just this one line takes care of it.
So basically, that is logarithmic. This one, right? Binary division, sort of.
Yeah, binary tree. Yeah. Well, is it binary or this one is 2? Or it depends. It's
Every
actually
time you're reducing by half.
Yeah, I mean, I don't know how it's implemented. Is it exactly half or 2 or 3 or 4? But it's a sum tree. Yeah, some.
Oh, it decides that chunk, that
Yeah.
4. Okay.
I'm not very sure. I haven't seen the implementation of OpenMP for GCC. Yeah, but something like that happens. Okay.
Okay.
So these are basically the 3 types of operations you have in OpenMP. One is the simple for loop, full parallelization. Then you have OMP critical for places where you want to make it serial because of to avoid some race conditions, or if that serializable operations are like just like this, reducible like this, you can use OMP reduction for reduction. There are other things called OMP atomic and all those things which are not usually required. It means if you have to do atomics and SIMD and all those things, you'll actually use atomic and SIMD lock, atomic lock, unlock, and SIMD you'll use intrinsics and so on. So you can play around with that. Means you can, if you want to learn more about OpenMP, first of all, again, you can go to the HPC repo. There are some videos there listed, so which sort of give you a good enough introduction to what all you can do with OpenMP. So if you finish all those and still you have questions or more things to discover, you can do a Google search of your own. Okay. But as I said, most operations, first of all, if you're using OpenMP, usually we don't use that.
Sir, what is the difference between atomic and critical? I didn't understand that.
See,
because in atomic also we'll do same thing, now like
atomic also will do same thing. Yeah. So for all practical purposes, atomic and critical can be considered the same. They're sort of equivalent for all practical purposes. If you look at the mechanisms under which it is implemented, actually, yeah, that also has lock, unlock, and all those. Yeah, so all for you can do a Google search and find what I don't remember. So OpenMP atomic versus critical. There's already a question. That. Okay. So. Oh, okay. Yeah. Okay. Good point. I haven't used this OMP for such a long time. I forgot these differences. So, okay, let's do this. Suppose my OMP, atomic and critical. So what Radhika is saying is that here when we wrote that serializable code, the critical portion, I wrote it like this. So basically whatever is inside this bracket will be serialized completely. Instead you can use atomic also. But atomic usually you don't do over a bracket. Because atomic basically puts a lock on the variable on which it is being called. If you call it on a bracket, there is no lock to put on a bracket. Okay. So you can use atomic operations only on one operation. Okay. Like this. If you need to do something like something else also, like for example, B, then you have to call atomic again. But if you use critical, it can be done within a region itself. You don't have to call it multiple times.
Okay.
So this is the difference. There might be differences in implementation and so on, but those are internal details. But anyway, so for all practical purposes, the way it works is the same. Yeah, we put in log 1, log 10.
Okay, sir.
By the way, reduction will only work. So if you try to reduce this, no, I don't even know, but this will work actually. It's fine. Let me check. Anyway, we usually don't use OpenMP, so I shouldn't spend so much time on OpenMP. Let's go to MPI quickly. So what we'll do is now, first of all, why MPI at all? If OpenMP is so clean and so simple, why the use of something called MPI also? The thing is, right now we were running systems which were taking up 1 billion 1 billion elements, and it is taking around 0.74 seconds. By the way, so as you can see, we have been able. Wait, what happened here? Did I put that? Huh, this is very interesting. Okay. Yeah, it's actually doing. Okay. So we were no, the thing is correct also. So we were trying to allocate 1 billion elements. So that is 8 GB and 2 arrays like that. So 16 GB of memory. Now suppose we want to simulate a system which has instead of 1 billion, 1 trillion elements. And in HPC like CFD and all those high resolution runs, you will easily encounter meshes with trillions of grid points and so on. Okay. If you're really doing high DNS level kind of thing. So obviously the RAM on your node is limited. So you can't even create the system. That is when you try to parallelize across machines also. So how do you do that? The first thing, the simplest way to see MPI is suppose I go into this node CN0161 and I give this run, copy whatever is there. Then suppose I go into the another node. So let me quickly misuse the queue and give a parallel run somewhere else also. Why am I so nasty? This is okay. This will actually, yeah, I configured it that way. You won't be able to use. Okay, fine. Let's assume that I am on this node, on the login node. Don't do this, but assume I'm on the login node, and I am on this node also. So I want to, if I have to simulate trillions of or 2 billion element array system, then I'll give 1 billion here and I'll give another run 1 billion here. Okay, that's the simplest way you parallelize things across machines. You give separate runs only in 2 different machines. But now the thing is, there might be some operation which will need you to know the values in this machine and that machine and make a sum. Like for example, we just now did that sum kind of thing. If we were to do this some kind of business, how would you do it across machines? So what you would do most probably will be you have this sum in this code. So then you will say, okay, for one code, I will say, why is this? Wait, something weird has happened here. This is not being able to go to this line. Oh, I think oh, I see. Wait. Log out of this node. So if I go to disk. So you're doing this something, and now if we are planning to run the same kind of code on another machine, suppose the login node here, we will call this sum as someone that for the run that is running in this machine, we'll call it a sum2, and somehow we have to add those two up. So when you're giving launching runs separately like this, MPI is a method where you can open a communication channel between the two independent runs. And only what you explicitly mention will get communicated between those two runs. So for all practical purposes, if you want a mental model of how OpenMP versus parallelization happens versus MPI parallelization happens, I'll just draw the crucial difference here. So for OpenMP, when you're launching the code, so when you launch it, you will be doing simple ./a.out with and you'll be doing that export thing also. So export OMP num_threads equals suppose 16. So when you do this, essentially what is going to happen is your code will first launch a single process. If you look at it top, you'll see there's a single process being launched. And then whenever you hit those pragma regions, which are hash pragma OMP parallel or hash pragma OMP parallel for any of those. So hash pragma OMP parallel. Whenever it reaches there, it will spawn multiple threads. So however many number of threads are there, you have suggested like 16 of them, it will spawn 16 of them. So I won't draw all 16, it will take a long time. Just draw this many, like this. And that will do the tasks which are inside the parallel region. So whatever tasks you have, that the computations, data transfer, and so on. And then when the parallel region closes up, like where the bracket closes up essentially. So if you want to demarcate that, let me put an open bracket here. And somewhere it will close the bracket of that parallel region. So at that point, it will kill all the, or basically merge all the children threads into the parent process. So basically the inverted version of this operation will happen. So I will just place that and do a vertical flip. Finish off. This is how it will work. And then after this parallel region closes up, you'll again end up with a single thread. So basically, it is a single thread process. It just bifurcates into multiple threads wherever you call OMP parallel, and then again merges back. So this is the main parallel processing region. Inside this region, you will be able to see all the data allocated by any other thread in your node or your machine. Okay, it's not like if I any data that was allocated outside the parallel region. So basically, if I do a malloc of an array here, all the threads will be able to see the malloc data. If something was malloced here, then only the thread which mallocked it will be able to see it. So anyway, so basically it is possible for you to share data very simply. You just define it outside your parallel region or allocate it outside your parallel region, create it outside your parallel region. That way it's by default shared. Anything that is created inside parallel region is by default private. So this is the OpenMP model. The MPI model is a bit ulta. What it does is, so here in MPI, what you'll do is, the way you launch codes is, you'll do MPI run -n, you'll give the number of processes that you want to run. So it will be like 16. And then you'll actually get the run. What this will do is, essentially, it will create 16 different processes. So basically, whatever is being done here, it will automatically launch from the beginning itself 16 different processes. And they will keep running as if they were completely independent. Only when there is a region where you call something like MPI send or MPI receive. it will try to communicate or build some bridge across these independent threads and make them communicate. So basically, if you want a representation of that, then essentially it will look something like this. Shit, it's a bit deep for some, but it all the communication double arrows. Okay. Yeah, so it'll create all kinds of communication inside that region. This to this thread and that. So you can choose which thread to which thread you want to communicate and so on. But it should happen within this region where you're trying to do OMP send receive and so on. Okay. Some like end-to-end communication will happen, end-to-end minus one. Okay, like this. And then when that send receive thing finishes, all communication channels are closed and the processes continue as if they were independent. So it will continue as if they were independent. So basically all these lines that we had created, they will continue. Only when the code finishes, each of the processes finish, they will basically end at the same time. Except that, yeah, basically they'll end at the same time. Or in one after the other, your code finally, this will show you your terminal again when the last one of them have ended. Okay. This is how it works. Okay, so is this sort of clear, the overview, what is happening here? This is by default a single process, and only when you explicitly call a parallel region, it will parallelize. This by default is a parallel thing. It's launching n number of processes as if they were independent processes. So if I was launching my copy code, like copy and 1 billion, 1e9, 10, each of these processes will behave as if I'm trying to launch 1 billion array size inside itself. So if I have 16 such processes, I'll end up allocating 16 billion data points in total. So usually what we do is we will take our whole problem size, which we would have sent to here, this OpenMP thing. Like here we would have done this thing. Here what we would do is we will mentally try to divide it by the number of processes and send only that much. So basically this will be 1 billion by 916, whatever that. So that will be, I think, roughly, I would say, that much. So this is, if you do this, then it will allocate 500 to the power 7 into 16. That is roughly, whatever, that 1 billion points in total across all processes. Okay, so now how does this MPI send receive thing look? So we will just quickly go into doing this send receive, and before that I'll just finish off OpenMP in the benchmark part. So we will copy this and save it. By the way, it's running fine, right? I don't know why this is happening. This is something very weird that is happening. It's lag in my terminal. Yeah, let's see. That's fine. No, it's not fine. Oh, because I'm doing plus plus. That's why. Fine. So this issue is done. I didn't mention which code to scale using OpenMP. So it was supposed to be the FD code, thermal code. Let us finish MPI, then we'll come back to the thermal code. Because once we come back to the thermal code, we will, I think we already have a merge request open. So we'll go to that, mark it as ready, and merge. Okay. So now we'll open an issue called MPI. It will close this issue once the pipeline passes. So parallelize across nodes using MPI. I think this main did not have. Okay, fine. We'll create two copies anyway, otherwise we'll do a merge conflict. So essentially what happened was it has still not merged yet. That's why the main doesn't contain the new OpenMP version that we have written in 10. And I branched out 11 directly from main, which contains something older than what is here. So when we try to merge these two together later on, might create a conflict if we're editing the same file. So we'll do a merge conflict there. Fine. Technically, you should wait for the pipeline to pass after merging. Okay. Quickly copy to a git pull. Out. Open. So in the benchmarks only, I'll create a new code, which is called, go out of this node, unnecessarily I shouldn't take up a node. So the copy example only, what we'll do is, we'll again go back to the serial version, so we'll call it copy MPI. So we'll try to create the MPI version from here. See, this was the old code. Fine, we'll just serialize this one only. And the one thing we did extra was reference value. A100. So this should work as it is quite fine, except we'll remove OpenMP. Now, how do you parallelize this? Parallelization, as we said, again, according to this model, if we launch it like this, it will just run independent. Just 1 minute.
Hello.
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 Okay.
What
Okay, I
happened?
thought something happened.
Okay.
Okay, let's do a quick sync check. So just let me know if the synchronization is correct. I'm going to write A, B, C, E. So MPI, yeah. So if I run, let's copy this code back. Let's do it in the cluster itself. That way, we'll just copy back the code when we require it. So, yep. I think I keep getting the same test queue node. Okay. No one else is using test queue, is it? So we'll make a copy MPI.cpp. Okay. So we'll remove the pragmas. We won't open MP now. This was the code that we had, and we'll just remove the bandwidth. Let's keep the bandwidth calculations fine. So this was the initial code that we had, and now if you have to parallelize, see, there is nothing to parallelize inside the code per se, because as we said, each of these processes will anyway be independent of each other. So you just need to like distribute the numbers. That's all. So essentially, nx, if you still want to pass nx as the total number, then your effective nx should be, so here your nx should not be this, this will be your total nx or total nx. And then you should say that your actual nx is total nx divided by the number of MPI processes. Okay. The way you get MPI processes is basically, or usually they're called MPI ranks, because it's like a, army with a rank of soldiers or something like that. Actually, no, they're called ranks for a different reason. So it's not called MPI rank, it's called MPI size, the size of the MPI group of ranks, basically. So MPI size, the way you get it for MPI code is, you just call MPI com size. Wait, forgetting all these syntax because now it is. And this function will dump it into this variable. So you have to pass pointer. It's not as cute as this. It isn't. Instead, it's a bit complicated. Looks a bit complicated because MPI was started by some US national labs in the 1980s, and they like C syntax of passing pointers around. So this is MPI com size, and the only other thing is you have to give what do you say, the MPI metadata for now, let's say, okay, which is basically an MPI communicator world. Okay. We'll come to this, what this means later on. So this is the function. So this will give you, if you launch the MPI code as 16 independent processes, then that number 16 will basically come in that MPI com size function returning. So MPI size will be equal to 16. So then you can take the total NX, which is 1 billion, and divide it by 16 and get your NX that you actually want to give to each process. And that's it. That's all you have to do in MPI, technically. Now the only thing is that it is an MPI code, you have to tell by including, otherwise where will you get this MPI com size from? You have to include MPI.h. And usually, if you want to send this MPI com world, if you have to use this metadata, you have to just fill in the metadata or initialize it by just saying MPI init. It's like it's initializing the MPI, all the internal metadata systems and everything. Even for no personal, it's okay. Doesn't matter much. And here, after you're done with your code, you have to delete a lot of this metadata that was generated. It can actually become quite large. So if you release the memory, it will be nice. Just like delete you're doing here, internally MPI panel also calls a lot of deletes. Okay. If MPI, by the way, MPI library, the way we use it now is a C library. That's why all these finalize and init and all those. If it was C++ code, there would be an internal destructor and so on. MPI had a C++ wrapper, but people found it so useless on top of the normal C codes that it was deprecated. So we don't use MPI C++ wrappers, or no one uses it anymore. C code is good enough once you get used to it a bit. Okay. So, and there's also a good example of where you can call a C library in a C++ code. So this is MPI. That's it. Okay. Just run it. Let's run it once and see what it does. So what we'll do is, as I said, this parallel process launching can happen. You can launch multiple processes in the same node also. On your laptop, you can run in like 2-3 MPI processes in parallel. Number depends on how many cores you have. But if your laptop has 2 cores, you can launch 2 MPI processes in parallel. Actually, it allows you to launch up to 2 into your number of cores by default. So you can launch up to 4 core processes if your laptop has 2 cores. Right? So, but as I said, again, the memory bound, compute bound arguments hold. So if your code is memory bound, you will launch only that many MPI processes as there are memory channels in your machine. Okay. So here we saw the best memory out performance comes with 16. So let's just reproduce those numbers again once. So we'll say copy MPI. So right now we'll just remove this sum business because that adds a bit of overhead. So we will remove that a bit. Without this, just the copy operation, we had got 34 GBps, right, from OpenMP. We'll try to see if MPI also gives you the same thing. So you're going to print the 100 value for each individual process, and then you're going to calculate the traffic. The traffic here is again, NX is the portion of data that this particular process, MPI process is handling, which is total NX by MPI size, so it's fine. And the other things are double and n samples and 3, so it's okay. And then the traffic by total time. And the total time here is just the total time taken by this process only. Okay. So we will give a run and let's see. So the way you give a run for MPI is, you can call Intel MPI also. So module load Intel ICC, we are anyway using Intel. And we were using ICPC for compiling the MPI normal code. When you're compiling for MPI, there are some special functions required by the compiler. So you call the MPI ICPC. Okay. Meaning everything remains same. Oh, by the way, you're not using OpenMP, so we can delete this. That's it. Oh, great. Oh, I did not delete all the OpenMP stuff. That is surprising. Where is it? Oh, sorry. Yeah. Good part. This afternoon starts happening, my brain starts losing its track. We'll overwrite copy only. Let's do that. I don't want to keep multiple things running around. So now for the copy executable, how you launch the MPI processes is MPI run. By the way, if you do MPI minus version, you'll see that you're using Intel MPI library. Okay. Like you need to do this because if you do this, how will you tell how many processes you need to launch like independently? So MPI run can launch independent processes like this. So MPI run minus n, which is 16, and then copy. And then how many? We'll send the total number. 1, 2, 3, 1, 2, 3, 1, 2, 3. 10. This internally will get distributed across all the 16 processes into 1 billion divided by 16. So let's see. So many outputs came. Basically, what is happening is each one of the 16 processes is trying to put its own output. So what we'll do is we'll just put the last or the slowest output. That is the worst case bandwidth that we're getting. Okay. So we'll just do copy MPI. So how do you find out which is this one which is the slowest out of all these processes? See, all these processes will start running independently. So somewhere you have to make them wait and you have to figure out which came the last. So there should be a checkpoint for a sort of checkpoint. So let it, and then only you will stop the timer. Okay. So the way you put checkpoints where all the threads have to come and wait till every one of the threads have passed is MPI barrier. And here you also put that metadata stuff. So this is basically like the metadata class MPI com world. So once you put this, doesn't matter which process came here first or last and so on, all the processes will have to wait at this line till each and every process reaches this line. Okay. Then all the processes will again start to the next line and so on. So essentially what will happen is, doesn't matter when we started it, when our timer started for each process, they will at least end at the same time, the timer here. Or if you want to be really correct, then ideally you should first put a barrier before the timer also. Because this different processes might take different timings to do this initialization. You don't want to count that. So let all the processes finish the initial step, let them synchronize, then you start the timer, and then you stop it like this. So we will just put it down. Okay. So this will give you the worst time estimate, but still every process is going to print these two lines. We don't want that. So what we'll do is we will just say that only if the process ID is 0, only then we will print. So what we'll do is MPI tells you what the process ID is. So something like MPI proc ID or something. If that is equal to 0, then only we will print this. Otherwise, we will skip it. With this MPI proc ID, usually you call it MPI rank. It's a conventional naming convention people use. Rank, again, the metadata of the whole MPI process or the MPI launch system that you use, and you pass it inside rank. The MPI rank will contain the process ID, MPI process ID. MPI rank. That's it. Oh yeah, right. Thanks. Good catch. Otherwise, I would have gotten wrong bandwidth and I would have again said, oh, it's too late and my brain is not functioning. Brain function will stop when it stops. Oh, achha, that's why it was showing you. Oh, I see. Okay, very smart. So we will launch. Now we see that only one rank printed. By the way, if you really want to see which rank printed, you can verify that actually the 0th rank printed. So let's say we print it here. Sum is this, and then we'll print the MPI rank also. And we'll print the MPI size also. So let's call it from rank equals, we'll print the MPI rank. Let's break a line. There's too many things in the same line, doesn't look good. Because there is that 80 character. Oh, by the way, I was supposed to tell people the coding conventions. Otherwise, major part of this camp is, we'll do it in the last 5 minutes of the day. A rank, and then out of how many total processes? Out of MPI size. It's a difference between endl and slash l. We'll get into it later. Okay, so as you can see, sum is 0. Oh, yeah, we are not doing the sum step. Rank 0 out of 16 processes. So there will be rank 0, 1, 2 up to rank 15. There's a total of 16 processes. And bandwidth is so low. Why? What happened suddenly? Okay, we'll see. Sorry, we'll come to code pinning and all those things. So it is showing one output, and it was trying to run 16 of them. So how do you now verify how many processes are running and what the value should be? So let us bring back, before that, let's figure out what the individual timings are. So instead of printing the reference value and so on, just to lessen the... Achha, by the way, just give me 1 minute. I'm trying to figure out some things quickly. This 136 is not supposed to be the correct bandwidth because we are not going to use double total time. Okay, yeah, total time. This is the total time we will have to sum up, no? Like, it's basically, I'm making a mistake in doing the theoretical estimate. This is the total sum. It is the individual process sum of number of elements, and this is the total time I'm taking. So technically, that won't be the full bandwidth. The full bandwidth you will get if you had put total here, no? But that will be too large. Maybe my timer things are wrong. Let's see. Then nx by MPI size, that is fine. And samples total. Oh, I see. No, again, this thing is trying to do some bakwas. Okay. When I remove this, no, it will try to think this is just a copy operation. So basically, when we were using hash pragma OMP parallel for, it was still trying to not do nonsense. So what we'll do is, okay, just to confuse the compiler a bit, we'll keep the hash pragma OMP parallel for here, but we will launch only one MPI thread. That means each MPI thread. So just ignore that hash pragma for now. It's practically going to be a pure OpenMP code. I'm just doing it so that the compiler doesn't optimize that thing away. But even that might not help. So total time. We'll print the total time also. We're printing that right. Yeah. Which is supposed to be correct. How much time were we getting in the previous case with OpenMP with 16 processes? Oh, sorry, not this one. 16 processes. 0.07, which basically means that correct. Not correct. How can it be correct? Anyone has any idea of what might be going wrong?
I also thought maybe you're not using A and then it's not calculated. But you're printing
that is one thing. Yes, that is usually the. No, so I'm printing A here, so it's not going to optimize the whole of it away. Figure out what might be the issue. Let's see. Total NX. Okay, let's do it with one process. This should get 33 Gbps. Huh? Okay, run, copy, one. Whoa, no, this is trying to do something really weird. Something is getting optimized away. So most of it is that only. So what we'll do is, just to confuse the compiler a bit. So basically what the compiler is trying to do is, it's seeing that, okay, I'm doing this AX equals BX for so many things, and there is pure C code here. There is no OpenMP or anything to stop. So it is trying to optimize something, and imagine that since I'm going to print A100, if I do something around A100, like only for X equals 100, 100, 100, around that neighborhood, that should basically suffice this guy's problem. Okay. And then it's trying to do that, but basically not doing a good job of it. That's why the number is saturating or giving me random numbers like this. So that is not the best way to do things. So what we'll do is, we will try to put some. The other ways to do it is, we can do an array swap. Let's do that actually. So what we'll do is, just to confuse this guy, we will say key, we are going to switch the arrays. Huh? So that, so we'll do a temp double star temp array equals A equals B, and then B equals temp. Okay, now I want to switch. This will not take so much time, so it should be fine. Oh, let's see. Let's optimize it away or not. Half the time you have to fight the compiler from doing nonsense. Okay, So, sorry, someone was saying something.
No, nothing.
Oh, okay. Okay. So basically, some tricky code you have to put so that the compiler doesn't think it's too smart. Huh? It listens to human beings still. I'm telling you, like if this is the stage of compilers, can you imagine how arrogant and irritating AI will be? So we will launch with 16 processes now and try to see if the bandwidth we are getting is correct. Before that, just let me quickly see the theoretical calculation once more. See, the bandwidth that we're trying to calculate, it is for per thread, okay, per process, because we are taking the data transfer of per process. If we wanted, so essentially, per process will basically see this only. So let's run it with 16 threads also. 16 processes also. We're seeing something like this. Okay, 21, fine. I'll tell you why it's 21. Why not 33 itself? So since each process is contributing a bandwidth of 21 independently, you have to sum up these bandwidths to get the total bandwidth that your machine gave you. So if you sum up, so 16 into 21, how much will it be? It will be 16, 21.4 into 6. 342, right? Which is perfectly the bandwidth that you got with OpenMP also.
You have to multiply the number of cores, is it?
Multiply by the number of MPI processes that you launched. Okay. Or the other way of doing it is this. When I'm printing, I will take the total NX. When I'm doing the theoretical estimate. So then it will print. So okay, let's do it like that. Then the total traffic. So let's do it like this. Let's not do it. We're anyway taking the worst case timing. So this is the lowest bandwidth across all the cores. So total NX, this is the total traffic. I just did not want to take the total traffic because we are making an assumption that we are distributing equally. In a real life code, you might want to give more load to one process and less load to the other, depending on if the two machines you're running the codes across. Suppose one machine was a laptop, one was this Rudra server. Obviously, you will try to balance the ratio out of the loads according to the power of the machine, right? So then you will end up giving, out of the 1 billion elements, you will give maybe 800 million elements you'll give to Rudra, 200 million you'll give to your laptop, assuming that the bandwidth of the two machines are in that 2:8 order or 1:4. Okay? So total traffic. So then, assuming it's equally distributed, total traffic is the total bandwidth then of the machine. So this is the total bandwidth. So now if I compile and run, it should give me 342. 342 APS. Okay, let's quickly copy paste this output so that we don't have a reference value always. Choose. Okay, I'm pretty sure there has been some confusion regarding this, so please tell me. Is there some part you want me to clarify a bit better? This is not the best example of OpenMPI. Usually if you go to MPI tutorials, people will do hello world with 16 processes, then it will say hello world 16 times from rank 0, rank 1 up to rank 15. But I'm assuming I think my network is a bit laggy. Is my voice breaking?
Broke for a bit.
Yeah.
Yeah, as you can see, latency went up here. It's going down fine. Okay. What to do? Okay, now it's fine, right? So let's look at the code and appreciate it a bit. And then whatever questions we have, we can come across. So the basic idea is this, okay, whenever in doubt, go back to this simple thing. We haven't done send receive yet, okay? So just independent launches of processes and how we are trying to manually calculate what the distribution of tasks will be and so on. And finally, we get the MPI bandwidth that we deserve from the node. Are there any questions or any portion that you are really confused what is happening in this portion of the code? Anyone? Oh, everyone understood, is it? Very interesting.
I think it might have, I don't know. Why multiply with 16? Why
Okay,
take over?
that one. Okay, fine. So essentially, why multiply by 16? Okay, that's a good idea. Let's go to this. So when we launch, the MPI process with 1, okay, let's rewrite the code a bit differently. What we'll do is we'll say that, okay, whatever input I'm giving is the input this code will take. MPI says this is no longer the case, so I'll comment it out.
Oh, acha, okay.
Okay, so if everything is like this, then I'll just comment on the total traffic also and keep it exactly the way it was for the OpenMP case. Okay. And this is bandwidth. And now I'm going to launch with one process. Time taken should be whatever the OpenMP one process time was. So we had that scaling, we had that scaling graph, right, on this node, where we had OpenMP to scale performance across threads. Yeah, this one. Someone's. Oh, okay. Oh, you want to say something? Yeah, say.
Oh, sorry, I got a call.
Okay. So one node we were getting, for one thread we were getting 33 Gbps, right, for the thing, and here also we are getting 33. Now if you go to two nodes, the way we rewrote the code right now, each node will be allocating a billion elements. So in total there will be 2 billion elements. Okay. And the way we are calculating the bandwidth for each process, I should not use the word node, I should use two processes or two MPI processes. So each MPI process will be allocating a billion elements, so total of 2 billion elements. And the bandwidth calculation internally, the way we modified it right now, will happen that what is the size of data that each MPI process is processing, and what is the memory bandwidth, what is the time it is taking. Okay, the worst time across all the things. I'm assuming that every process is taking the worst time because I put that bad here. Okay. But every process is taking that worst time, and then we're trying to effectively calculate the memory bandwidth per process. Okay. So basically, if there are two processes that are going to run now, then there will be one process running here, one process running here. So effectively, this process will be transferring data through this one, and this process will be transferring data through this memory channel. So each process will show the bandwidth of one memory channel. And then if you want the total bandwidth capacity of this whole run, then you should add up the different processes together.
Yeah.
So if you do 2, it should become twice of 33, 66, it should become, or 65. What? Oh no, yeah. So this is the individual one. Yeah. So ideally, if you really want to see how it looks like, so, sorry, copy MPI. So ideally, I should not comment out the other ones. This MPI thing, no? What I'll do is, see, I cannot, okay, let's keep this, fine. Just that we will put a nice barrier, like distinction mark here. That way we are able to see which process is printing separately, which data. Yes, once multiple processes print the same thing, it might become a bit difficult to figure out. And this MPI if condition I'll comment out so that all processes will know print. Oh, sorry.
If I give more than 16 cores,
No, so as we were seeing, no, and for the OpenMP case also, more than 16 will start to decrease performance because it's just getting clocked.
So give the maximum number of channels.
Yeah. So one process will print something like this, 33 Gbps. So actually, you will see that the time taken will remain the same, even if I do two processes, because the data size per process is remaining the same. So this is an example of weak scaling, what we are doing. The OpenMP thing that we did was strong scaling. We can do strong scaling here also, I'll show how. But this is weak scaling. So basically, when you do weak scaling, it's there's the problem with MPI. And this is a good example of what a race condition looks like. So one process tried to print this, and in the meantime, the other process started putting to terminal its own thing. And then you can see it's a full interleaved kind of output that has come out. Okay. So usually what you do is you do it process by process. But if you just do one line, it will be fine, I think. Just let me do it. The ideal way to do it would be just comment one line, like just ask it to write only one line. And you put an endl at the end of it, and it flushes properly. This /n doesn't flush the buffer, the display buffer, the stream output buffer. So this thing, but again, the compiler will try to act smart because we are not printing 100. So what we'll do is, instead of printing 100, we will just say key if 100 is negative, then you say error out is got found error. Okay. This most probably won't get triggered. That's why it won't say it. Okay. Let's see. Should be 33 plus 33. Okay. This also didn't help, but okay, at least we got 33 here, GBPS, and 33 GBPS here, which adds up to 66. Sorry. Oh, we should have printed that Intel's nice scaling. Okay, fine. We'll do it later. So anyway, as you can see, it scales nicely. Both give 66. So now the thing is, instead of doing all this, separate manual adding up of things, why don't we see how? So this is weak scaling. Huh? This is an example of weak scaling. That individually, you are taking the same problem and cloning it across multiple thread or processor threads. Huh? So let's now instead do the normal strong scaling that we were doing with OpenMP itself. So basically, I'll keep the system size fixed to 1 billion elements, but I'll distribute across multiple processes, MPI processes. So we'll come to nx equals total nx, the way we were doing it previously. And int nx is total nx by MPI size, that is fine. Time taken is same, this thing is fine. And we'll put a if condition. And the theoretical calculation of the bandwidth will be now total nx. My total time is basically the worst time across all the processes. And this is my total bandwidth effectively. Okay. So now let's see. This should give me 66 directly for this run. Because I'm going to send the same system size, but distributed across multiple processes. The time should half now, but bandwidth should remain 60. Total of it should give 66. So just check if the time halves. It should become 2.4. Huh? Oh, did we not compile? Oh, sorry. Ah, 2.4. Okay. And 66 is the bandwidth. Now we can give a full 16 process run and see. Okay, let's do scale by scale. 4. Scaling 66, double of that is 1, something. Correct. And this is time halved. Okay. This is strong scaling we are doing. We're taking the same system and distributing across multiple processes. Halved again, time halved, bandwidth doubled. Great. 16. Great, 342.46. Brilliant. 32. It should almost be the same. Okay, fluctuation. Now it should start degrading. See? and then 128. Final duration. So this is how MPI also scales. The only thing is now, since you have written your code in MPI format, you can parallelize it across nodes also. So how do you do it? So for that reason, I'll just exit my interactive login node and go into a submit script. Huh? So if you want to sample submit script, I'll just copy one from the repo. Systems, Rutra cluster, how to submit. You can beginner job submission script, which is good enough for me, beginner. So I will be using, so this is my wall time. I need 10 minutes maximum for this. My MPI run. I don't know if you can use this. Let's use this. Here you can. I can go up to 2 cores. Here I'm using test queue, so 2 nodes I can go up to. And in each node, I will spawn 1616. So I will be utilizing the maximum bandwidth in each of the 2 nodes. And since I'm using 2 nodes, I should get 340 plus 340, which is 680 Gbps in total bandwidth. So we will, instead of loading GCC, we will load Intel ICC 18.0. And I am going to go into my this thing. Expert desk. This is not the best way to do it. As you can see in the next robust job submission script, you can just use the environmental variable work there, which automatically sets the folder to the folder where you will launch the queue submit command from. So let's use that, and then we'll load 18, this thing. So we'll compile. Usually people like to compile outside, like compile in the login node and then submit the run directly. So we'll do that also. Let us handle our compilation outside, not compile and submit at the same time. So MPI run, NP. So now see, there are 2 nodes. Each node we will run 16 processes. So there will be a total of 32 processes. So which is 32, happens to be 32 here. Okay, so we'll run 32 processes totally. How do you determine across which 2 nodes it will run and so on? That this PBS job scheduler will take care of. You don't have to worry about it. Okay. Because it will find internally which nodes are free, which has what wall time and so on, and it will assign you proper nodes and so on. So you can run like this. And then we'll put copy 1 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3, 10 iterations. Okay. This 1 billion will get divided across 32 processes. So you can see how many processes, how many elements each process will take. A little less than 1 billion it will be because I've done an integer division there. So just round off the number a bit. So, okay, that is it. That should work. Yeah.
Here, when you give 16, there are actually 128 cores in this, no?
Yeah. So this is the number of idle. Yeah.
Yeah. Okay.
You're saving power. You're doing the environment a favor.
Okay. Yeah. Right. But will the other cores in that node be of? Will the other jobs pick it up?
No. The moment you put scatter and exclusive for EXCL,
okay,
it means you have reserved the node. Yeah.
Okay. Okay. So the node is okay.
Yeah, it's reserved for you. Yeah. Means that's the thing. So see, if you hire HPC or if you rent out a node in AWS or Google Cloud or Azure, no, there they do it just to increase their profits. They will.
Okay. Okay.
They will try to put others' jobs if your node is free with some cores and so on. That's not the best thing. Because see, people will be paying by the number of cores. But if their job is compute bound or memory bound, they should actually pay by the number of memory channels, no?
Correct. Yeah. True.
So these are all Amazon will not say, because otherwise how will they make profit? So I think someone had asked this question, why do we not run our codes on Amazon and so on? Why have your own cluster? You can have your own cluster once you know exactly what you want. If you're trying to first do some test runs and basically burn your hands in the experimentation process, then fine, AWS is fine. But after 1 or 2 such hand burnings, you'll realize that it's actually much less costly and much better performance wise to run your things on your own cluster. The only good thing is if you have very fluctuating workloads. For 1 month, you have hardly any workload, and suddenly one customer comes and says, I want a 128 node run. Then you can't suddenly go and say, okay, I have to buy a 128 node cluster. Then you can rent on the fly 128 nodes from Amazon and run. So for flexibility, they're good. For if you have a steady stream of jobs like we have, our cluster is always busy, then it's good to have your own cluster. It's much cheaper and performance-wise also better because we don't run things inside containers. Every node on Amazon will be containerized in the sense that if you want to log in, you'll always log into either a Docker machine or some virtual machine because they can't keep reinstalling the OS as per the user's need on the bare metal server. So they will always give you a Docker container of whatever image you want. And Docker basically reduces the performance a bit in some cases. Okay, so we will run this. So QSub submit. Oh, project, sorry. So usually for internal things, we call it internal, but you can call it something else. Submit. Supposed to print a copy of this. Here it is. This is output. What is the output? 683 across 2 nodes. So you were able to effectively double your bandwidth compared to a single node. This is how you give larger job across nodes, or if you have the same job, you can finish it faster, 2x faster. If you use multiple nodes. Okay. This is basic MPI. Now, if you really want to go into some fancy things, you can also bring in that previous thing that we were doing here, sum. I want to sum all the variables across nodes also. So in the end, I should print that 2.5 into 10 into nx. How do we do that? Then we will see. Anyway, I'm summing up here. Okay. Inside a MPI process, anyway, it's serial. Inside the process, it's serial. I just have to communicate or average or sum up across nodes as well. The way you do it is you do MPI reduce. In OpenMP, we used reduction. Here it is reduce. Here, you will basically have to tell MPI, because it is a C library, it has a lot of pointers coming in, coming out. If you wrote in a C++, there will be a better way of writing things, but because it is legacy C, it is like this. The first argument will be the variable which you are going to sum up. So this is the sum variable of this process. Then you have to give the variable, which is the global sum in which you're going to collect. Then you have to tell how many items you're passing. In this case, I'm passing only one variable. If you're passing an array, you have to get the array size here. So it's one variable. I forgot after that. What is syntax sequence of things? So my favorite code, COM1 is it now? And which is the gathering process? That was also there, no? Root process. Is it root and then COM1 or?
Yeah.
That's why I keep getting so confused with this. My favorite documentation for MPI is Dino MPI. It's a Windows MPI for Windows, but the documentation is nice. So reduce. If you go for, you'll see the signature function. And they also have an example. So you can run this example also to see how it works. So this documentation, in every case, is an example. This is a good documentation. So send buffer, which basically means what is the pointer to the sending variable, the variable you want to sum or send across. Then receiving basically means the variable will come across as send, receive, and all these things a little later. What is the variable you want to gather it into? The sum, accumulate the sum into. Then the count. Count means how many variables I'm sending per process. I'm sending only one sum per process to the main accumulation counter. MPI data type, oh, that is there. So MPI data type here is MPI. What is the type of the sum? It's double. So you say MPI double. Again, there's a reason why they want separately. Why can't I just write double, or why can't it infer from the variable itself that it's double? All these are good questions, but unfortunately it's legacy C code, so don't ask these questions. MPI op after that, which is MPI, we're trying to do what? Sum. If you were trying to do subtract, then I think it will be MPI sub or something. Find out the MPI ops somewhere. There'll be a list of MPI ops somewhere on the net. So you can do min, max, and all other things. MPI op. What is it called? MPI op. Oh, this is. This is the thing. MPI sum, MPI prod, MPI max, or something like that. Okay. These are the common things. There will be MPI min also, MPI sub, and all this. MPI div. Does it division make sense? I don't know. So MPI add or sum. And then we have root. Root basically means into which mother process are you going to accumulate all your accumulate this global sum variable, or where does this global sum variable reside? So each process will send the sum variable, but some process has to accumulate it, right? So which is that accumulating process? So we call it as root process. So root, I would say, is MPI process 0. Okay. You can change it wherever you want. Usually people use 0 as the root process. So it's guaranteed to be there. Because if you launch one process by default, that is 0 process. Process ID 0. So, and MPI com. MPI com is basically that metadata stuff that you keep sending to every function. MPI com word. We'll come to that. That is a bit advanced, so leave that for now. Or usually you will see people do this. If you don't want to keep writing MPI com world and so on, you do MPI. You just store it locally in a variable called MPI com and call it MPI com. This is equal to, you initialize it with MPI com world. So now your metadata is contained in MPI com. So you can just keep writing the shorthand syntax everywhere. So we'll do that. So why am I doing all these things? This Vim. And now you have seen everything has been replaced, including this itself. So let's just. Okay. So, yeah, you're doing a reduce. Now, the thing is, these are supposed to be pointers, not actual variables, because if you send the variable itself, then it won't be able to return you the value in the global sum. These are to be pointers to the variables. And you define global sum. So double global sum, you can initialize it to 0. I don't think it matters actually, yeah. MPI matters. Preferred open matters. So global sum is this. Your sum is anyway defined above for each individual process. So you can think of this as the local sum. Local sum is local to each process. The global sum is the accumulated total sum. That's it. Now, if you want to print, you should print the global sum. So we'll go back to printing and we'll print the global sum. Sum only. And this should be equal to how much? 2.5 into 10 to the power 9. Huh? Because, no, 10 to the power 10. Because we're using 1 billion elements and 10 iterations. But not 10 iterations here.
Now traffic is 3, no? Now one more rate.
Yeah. This will degrade the performance a bit because now we will actually see how much it is. Yeah, good idea actually. Let's see how much it will be, because we are not using OpenMP's reduce. We are reducing it ourselves serially per process. So technically it should give me still 342, but we'll see. It might not. Depends a bit on the optimization that the compiler is doing. Fine. Oh, we are submitting things. Is that? So the script is the same, nothing much to change. So we'll just delete the previous runs thing. Let's not dirty our folder with all this output files. So, it's already done it. Oh God. Yeah. Not coming up, huh? Reverse switch. Okay. Fine. Oh, modular F2. LICC. And MPI ICPC minus 03 minus STD 11 and copy MPI. That's minus over. That's it. Already, huh? See, bandwidth is correct. Good enough. It's actually a little more, no? That's surprising. Is it or a little less? How much is it supposed to be? 320, 340 into 2. Oh, a little less, huh? Okay, that's fine. Because that local sum, how it is being stored internally is a bit tricky. And you have trivial part 10. So basically you have gathered this data across nodes now. So this is the first calculation you're doing where you're communicating internally across nodes. Now this reduce might seem a bit of a black magic, and the way what essentially MPI is trying to do is inside this reduce thing is this. There are multiple steps going on inside reduce. For each, so if I just try to write the equivalent way MPI is trying to do it is, for each process, MPI will first send this local sum to some variable called global sum on the root process. Okay, so basically from my rank, so from MPI rank to rank equals 0, it will send this. Okay, so this is from local sum on my rank, it will send to global sum on rank 0. This is the way, this is pseudocode, this is what it sends. And see, it might send, but if rank 0 doesn't know something is incoming, it will not even open its firewalls and try to receive it. Okay, so in rank 0, then you have to say that you should be willing to receive something. So receive something coming from local sum, from the variable local sum on that rank, whatever that is. Okay, rank something, rank suppose 4, and write it down to my some temporary sum, because that is technically it's only one value, so it's not the global sum, it's a temporary sum from 4, from 4 on my rank. Okay, so now this will operate on, this will be called on all the ranks, including trivially on the 0th rank, and this one will be called only on the root rank. So if you'll do something like this, if MPI rank equals 0, only then do this receive. Otherwise, other ranks are not trying to receive anything, they're only trying to send. And do it for all, like try to receive from all the ranks. So you will do int I equals 0, I less than MPI size, I plus plus, from, now let me quickly check what is the syntax of receive. Thank you for getting that. If you use the SLabs core library, you don't have to do all this because there everything is C++ templating and so on.
Hey, in the core, why do you give 0 equals, if 0 equals MPI rank?
Okay, good question. This is another anecdote. Microsoft actually had to suffer a $3.2 million loss because of this problem. So,
Okay. Crazy.
Arbitrarily, you might, when you're very sleepy, instead of this comparison, you might do something like this.
Okay.
And the code will compile and go through. It won't raise any error, but your answers will be completely wrong because MPI rank equals 0 is an operation which will set MPI rank to 0, but the return function of that is true usually.
Oh, okay.
But now if you try to write it ulta, like this, if you write something like this by mistake, there will be a compilation error because you cannot assign something to a constant value like 0.
Okay. Oh.
This loss that Microsoft suffered, they found out this was the reason that someone has done this.
Okay.
They did not do it for MPI, they did it for something else. But as a coding principle,
yeah. Principle. Okay. Oh, so what you're comparing to, always keep it in front.
Basically, always try to keep a constant value in front.
Constant value.
So that if arbitrarily, accidentally you write something like this, then it will
Doesn't-
raise a compilation error. Yeah, you cannot assign something to a constant.
Okay, cool. Thanks, man.
Yeah, that's a coding tip. So okay, the funda is here that you are going to do a receive from each of the sends. Okay, from each of the other ranks. So anyway, you're iterating of the ranks, which is I. So you're receiving onto your buffer. So my buffer here, I would say is, so I'll have to create a buffer for receiving all the temporary values. So I will call it temp sums from all the ranks. These sums are double type, so I will call it double equals new double MPI size, because I'll be receiving one value from each rank. This one I'll do free here itself, because I'll be and now when I'm receiving, I'll send the rank of like I'll store rank i's received value in temp sums I. So what I'll do is I'll say temp sums I'll receive in count is 1. There's only one value I'm receiving in from that process. This type is again MPI double. Source. What is this ID rank of the or process ID of the source originating message? This is the sender. So this is I. This I is sending to me. Tag is some leave it. Tag is basically if the same source is sending the same kind of MPI double and count 1 to me only multiple times, then to distinguish between those two messages, I can use a unique signature in the tag. So let's call it 1, 2, 3 or something like that. Okay. As long as you're sending only one message from one rank to another rank uniquely, it's fine. The tag is useless. Only to distinguish between same signature, other signatures remaining the same, you're sending the same, then you use tag. Okay, and communicator is that MPI com metadata. And then again, like MPI looks hard because it's of this kind of weird syntax, but this syntax is a standard syntax that you'll see in any C library, because there is no object-oriented programming or classes encapsulating functions and all. So it's always weird global functions like this. And status. Status is something you can just send as MPI status null or something. What is it? What do you people use usually? Okay, fine. Let us keep a status. Okay. MPI status basically gives you a token of acknowledgement that if it receives, then the status will be correct. Oh, okay, received. Otherwise, it will say I'm still waiting or something like that. Or there's an error during the send if the message gets dropped on the way. If it's traveling over Ethernet, someone comes and cuts the Ethernet cable, then it will say status is lost message or something like that. Okay. So let's call it create a status flag like this, and then you send the status for the status here. I think you have to send by pointer. Again, in C, most of the variables are by pointer. Okay. So this is what it does. It receives. Then here it will do a sum. So there will be a double. So let's keep it outside. Or actually here only we'll put it as double global sum is 0, and now it will just run over the temp sums, sum of the temp sums. If you are used to using C++ STL containers, you could have used std vector here instead of this new and delete business, and then you could have done a nice accumulator std iterator to accumulate. But we are old people, so we'll for now use the old syntax of doing it ourselves. Later on, we'll go into STL containers and all those things, fancy things. Fancy things eases your life a lot. It makes C++ more cute, as cute as Python. Yeah, and then you will print your global sum, but the global sum has been printed outside here. So what we'll do is we'll just escalate this to outside the scope of this MPI rank 0. Oh, we already have it there. So this is it. So this is what is happening on the root process side, rank 0. And all other processes are going to, okay, fine, we have to, this pseudocode, we have to flesh out this one also. So let's go to send. And it says, what is the value that you're going to send? So let's put that quickly. So we are going to send the local sum. So point it to local sum. And then we're going to send the count of the data type and destination is, what is the rank of the destination? So we are going to send to the root process, which is 0. And then the tag, it should be a matching tag, otherwise it'll complain that it's not matching. So 1, 2, 3. It's like an acknowledgement that this is the message I was looking for. So this should work. If it doesn't work, I'm going to give up here because it is already past almost 4:30. Let's compile. Oh, why I didn't? Oh, okay, later. So since MPI size, MPI rank, and MPI comma are very frequently used in MPI code, usually it's a good idea to define it at the top itself, so that later on you don't have to go searching where did I define it, where did I define it. So usually people define rank. So aesthetic choice. Rank out of size is usually the convention people use, so rank comes first. Okay, now we will click submit and we'll see if we are getting the same value as the previous one. So I think it should work. I don't see why it should not work. We'll see once the error comes. Who is going to bet that this is going to contain an error? 10 rupees bet. Hey, what is happening? Oh, it's not even going to run, huh? It's stuck somewhere. Where can it be stuck?
Hey, there should be a barrier, I think, for MPI receive in that for loop, because otherwise everything is running that for loop, and in that for loop. So basically every process is running this for loop, right? So
no, only the first process is running. It's if MPI rank 0, right?
No. Okay, that I is. Oh, okay. I was confused with that I.
Actually, you're right. There should be a barrier because only after I receive, it should.
Yeah. But yeah, I was confused the other way. Okay, but I think there should be a barrier because otherwise it won't have sent. No, it goes in this.
What? Okay. So what? Okay. Let's look at an example here. Here it is. What it's trying to do is, if rank is 0, it will send. If rank is 1, it will receive. Wait. First of all, let's see if it is finished. Sorry. So basically, it's stuck somewhere. So this is the first kind of error that you'll definitely get in MPI once you start programming. Is you're trying to send and receive something where it seems to be stuck somewhere. So now the question is, where is it stuck? This is so let's do it with 1. We'll go into our log into our node. First of all, let's kill it. Otherwise, unnecessarily it will be stuck somewhere. It's keeping on running. Let's delete this code. We'll debug it inside the node with a 2-process setup. Oh. So, as usual, module load until cc. Oh, it finished. Oh no, it got killed. That's why. Sorry. And if it gets killed, you'll get a weird no message. So let's debug using first of all, one run, like one node, one process run. So MPI run minus n 1 dot slash copy 1 2 3 1 2 3. Let's do it with this only and 10 iterations. Surprising, even for one process it is stuck. Okay, so what is going wrong? Does anyone have any idea where it might be going wrong? For
The MPI send should be in. Oh, you've given the entire thing in. Like let's say first process, it's sending to 0th process, like as in the first local sum.
yeah,
Then 0 rank will receive it, but the others have already sent.
yeah,
Others also, like everything sends at once in that MPI send, no?
yeah.
So, but receiving is happening sequentially.
Yeah,
Okay.
that is okay. That is, I think, okay. Like that.
I think shouldn't it send, receive, and then go to? Can there be multiple sends and receives in?
Yeah,
Right?
Number of sends and receives should match, is it or not?
yeah, that is true. That should be also the case. Otherwise, it will start throwing errors or get into a timeout barrier. Let's do one thing. Since the single process case itself is failing, there is a simple possibility. So let's try that once. Huh? Just give me 1 minute. Compile this code and run. I don't know exactly what the error is. But yeah, these are standard MPI errors, which everyone will come across once in their life or multiple times in their life. MPI ICPC. And we'll run. Okay, still nothing. Okay, so let's see this again. Let's see where the code is going wrong. Well, let's move all these fancy things. Wait, the status, can I just say status null or something? Status is bothering me. Status ignore. I want this to come finally to a single line. So okay, so what we're trying to do is we're going to send. So let's comment out this part. We'll just take out here. Let's try to see exactly what the send receive business is. Like this. First of all, okay, now even before you start debugging, first you have to know where is it failing. Okay, so it's always a good idea to put prints. So see, you can do it using a debugger and all those things, but the simplest way is so sending sent, receiving and received. And here we will just take it into a some variable local like acom. So,
That I should be.
which one?
I in MPI receive. You have that I should be.
Oh yeah, right. I'll change that. That will be 0. Yes, because I'm going to run onto one process.
Okay.
Count is 1, MPI double, MPI status ignore. Looks fine. Shouldn't be a problem. Will there be a problem? Obviously, there will be a problem. How can it not be? It's past the time. See, after 4 o'clock, no, people start cursing so much. Why is this guy taking, taking time? All this curse comes and hits me. And then all the bug starts coming in. So, we'll just compile and run. Sending, it's stuck. Okay. So thing is, stuck at sending itself. That means there's a problem with sending itself. The question is, what is that problem? Any ideas? Anyone? Let me quickly check if the syntax is correct. Correct only. People who have done MPI before, please help me out here. I'm stuck.
I used to just put barriers everywhere, dude. But yeah, here.
Is it processor is trying to send before some is completed for some processes? Should we put barrier?
Here, see, I'm running with a single process, so it should be
Oh
serial.
yeah, exactly.
Yeah.
Interesting.
Interesting, no? So let's do one thing. Let's launch with two processes and go back to a simpler MPI example. If my rank is 0, if my rank is 1, only then I'll send. By the way, if my rank is 0, only then I'll send to process 0. Else, this won't make any sense, but okay, fine. So basically, you now split this message also into 2 parts. Huh? And bring it inside. Just stop me if you think I'm doing something wrong. Else, if my process is 0, then I'll only receive. So accumulating sum, I'll be receiving from, so there was the syntax, send will send me to the destination, so data type and destination is 0, and receive will tell me which MPI process to receive from. So receive is here, little source. So it will receive from 1. And I should launch a 2 process system. Work. Okay. Let's try that once. Compile and launch. Let's make it even smaller so that it finishes quickly. Finished. How did that happen? Okay, so the thing is this. All this drama, I'm very sorry to do all this drama at 4:30 after the schedule is supposed to end. But the thing is, this is the fundamental concept. If you get this concept, MPI will become very, very simple. MPI send and receive are called blocking operations in the sense that when send is trying to send to some other rank, it will not release its send function unless the other rank acknowledges it. Now the problem is, if you it's like trying to hit a self goal, which MPI hates. If previously what we were trying to do is we were trying to send from process 0 to process 0. Now, as I said, by definition, MPI send is a blocking process. So MPI send will say, okay, I have to send this message, local sum message to process 0. Means basically if the setup was something like this. Or in the previous case, so this if was not there, it was just plain. So, okay, fine, let me just comment this out. Just to show you what was happening previously. Previously, this was the situation. Source is 0, destination is 0. So MPI send will try to send to 0, but it will not quit finishing this function unless the receive has been acknowledged. The problem is receive won't be acknowledged unless the actual send function finishes. So this, for blocking communications, it is very difficult to send to the same process. It will block. And if you are going to do a send receive communication using MPI send, MPI receive, always ensure you are doing it from a process to a different process, never to the same process. And again, just imagine what all pitfalls your blocking communication might go into. Like, for example, I'm trying to send to another process, but if that process is trying to send back to me, then I'll go into a cyclical lock again. So these kind of locking, blocking, and synchronization mechanisms tend to make MPI operations. That's why, apart from that, there is also performance reasons, but it is always much simpler to imagine to send something called non-blocking operations, which are I send and I receive. Whatever we were trying to do, I think we are very much used to doing non-blocking operations. Like this is also used in JavaScript and most web development languages. All are non-blocking operations in the sense that I will send. I won't wait. I will send my message and assume maybe the whole cluster will take care of my message. It's like, it's not like you stand near the mailbox after you've deposited your mail for the post office to carry. No, you will dump it and come back to your home. Let post office take care of it, and it will reach its receiver someday, and so on. Send is a very, overly attached kind of person. That I will wait here near the post box till I see the mailman coming and then taking it in the car and then delivering it. Only after I see it has been delivered, I'll come back to my house. Okay, which is very. So basically, if you are trying to send yourself the same postal message, you won't receive the message unless you go back to the house yourself. So you'll be stuck standing near a post office for eternity. That's why it went into a lock. So we will try to use the non-attached or very, ascetic kind of function, which is isend, which is a non-blocking thing. Isend will just send. It won't wait anymore after sending. So let's look at isend's thing. So there's a buffer, which is fine, which we have. Count, data type, destination, tag, com. There's something called request. We'll see what this request is. For now, I'll just create a data type called request. How is the data type? Like this. Just copy paste. I'm tired of typing right now. We'll create a global request. So right now, this would have blocked. No? So just to drive home the point again, this would go into a stuck loop if we are compiling and try to run with the 0. Sorry, not 0, 1 process. Huh? It will show sending, stuck. Basically, your process 0 is now stuck at sending, trying to send, waiting. When will I get the receive acknowledgement? But receive acknowledgement won't even start because it's a serial code. So this function won't even be called until this finishes. It's not finishing. So then we will use isend and see how the same function, if you make it non-blocking, this will pass. So we'll put a request here. So this is the send request acknowledgement. So usually the post office gives you a token, no? That this is your ID, tracking ID or something. So this is the tracking ID basically. And receive request. Similarly, there will be I think there will be a receive request. I receive as a receive request. So we will put, and does it have the status signal? No, not status. So here it will also give the client a receive request. Not request, what am I saying? Receive request. Basically, it's like an acknowledgement that you received it. Sign here. You received it. Okay. It's exactly like the postal service or courier service. Okay. So basically sign here. Huh? So we'll have to create those requests. And then see, because both are non-blocking, it's very difficult to say I send and then put a receive on that. We can try that, but let's not do the experimentation right away. Let's do I receive here. Actually, let's do this thing. Let's see what happens. Feeling a bit frisky today. So this was receive had MPI status ignored. Right or no? Did not have. Receive. Status ignored. Okay. I see only. MPI status ignored. Fine. So suppose I do a non-blocking send and then try to receive that message. What will happen? Let's see. I don't know. I haven't tried that in a long while. I forgot. Passed. Okay. So basically it sends. So let's try it out. Do you want to try it out in real life? No. Okay. So this works. So basically you send, and after it sends, it doesn't care whether it has received or not. But this guy is still blocking. So it will care that only after I receive will I let myself go. So then doing a non-blocking send, but doing a blocking receive is fine. But if I again go back to doing a blocking send and non-blocking receive, I'm again screwed because there's no point of doing this because send itself won't let me get out. It will be stuck at sending only. So let's try that out once. So this will require a receive request. And here I don't need anything for non-blocking, for blocking. Actually given an error. Timeout error. You wait for 5 minutes or something. Okay, don't wait for 5 minutes. Send is also itself not releasing its package. So what to do? Or it has released this package, but it's waiting for its acknowledgement, which will only happen once this gets it. So usually what people do is they use I send, I receive in a pair because it depends. You can use blocking and receive, but if you really want things to be very loose, like let post office do its job, I will receive when I receive, I'll send when I'll send and forget about it, I'll receive when I get it. This is the philosophy. Like don't keep calling the courier service or post office every day. Okay. So I send, I receive, then both have to have these requests and these token acknowledge. So see, if both parties are saying I don't care, that I'll send it and forget, and this other guy is like saying that I won't even bother about receiving the parcel unless it comes knocking at my door, then how do you even guarantee that the thing has been transferred? Okay, like if I send and forget, suppose someone came and cut the Ethernet network, then obviously my packet got dropped somewhere. Then receive will not even care because it's anyway not bothered about receiving anything. Like only if someone comes knocking at his door, it will open the door, kind of thing. Okay, so then the only way to deterministically or guarantee ensure that it has been received is to verify that both these tokens that you collected from the sender, like tracking number that the sender got from the post office and the signature that I actually received it, you verify that those are correct. Because if either of the signatures are wrong, that means something wrong happened in between. Either the road got blocked or your wire got cut or something like that. Okay, the way you do it is you wait till all the requests have become valid. So here you will essentially do something like wait all signatures. I'm really sorry, I have to keep looking these up because usually when you use that SSLabs code library, all these are taken care of for you internally. So I've stopped bothering about this one. So you need to tell how many tokens you're waiting for. So in this case, one send request, one receive request I'm waiting for to be valid. So 2 such tokens. What is the status of those tokens? So you have to give a, an array where it will verify and give you the like the output of that verification. So the status will be correct if the send request is, or status 0 will be okay, or true if send request is valid. If it will be false or some weird error number, if the send request had some problem. Similarly, status 1 will have the like validity of the receive request. Okay. So you give it an array. Sorry, create an array here. You can be static array, it's 2 only, it's okay. You know it's beforehand, it's 2. So, and then you send the request. Now the thing is how I have to send the request as a pointer array again. So what I usually do is, or what people usually do is, they create the request also as an array. It looks nice also. Sending is request 0. And receiving is request 1. and just send this array. And the whole program will keep waiting here till both the requests come back in a valid state. Or if it comes back in an invalid state, it will throw an error and exit the program. Okay, so let's run this code. So much gyan I get. Now if I get an error, it will be, oh, thanks. What is the compilation status? Oh, okay. What?
Pre request 0 and request 1, right?
Uh,
MPI wait all.
See, MPI wait all signature is array of state. Oh, acha ulta, array of request and array of status. First, it will take the request and then give you the status, obviously.
Okay.
Ulta. Please go through, otherwise, if I have given so much gyan, very nice. Okay, so this is how MPI works. Was this clear? I'm pretty sure there will be thousands of questions now. Please ask them, and I won't take much of your time. Just ask them and leave it to me. I'll send out individual customized emails to everyone, whoever asks. Or we'll discuss this tomorrow morning. So can we take one first half session tomorrow morning? Do you have anything? Just to finish this part, MPI is done. There's nothing more to MPI than this. Like few sugary coated syntaxes here and there will be there, but the basic concept of MPI is this: send, receive. Again, going back to the slides, does this make sense now? That each of them is spawned as independent processes. The only way you communicate data is through the send receive mechanisms, or I send, I receive, and then let it be. Whenever the I send, I receive transactions are completed, it continues as its own independent process. The other thing is, the other major difference is MPI one process, since it's like an independent process, won't by default be able to see the array or variable contents of this process unless you explicitly transfer the variable to the other MPI process. Okay, that is why it is called a distributed memory paradigm, where each of the processes have their own allocation in the RAM, which is invisible to all the other processes. Here, it's a single process which is spawning children thread. That's why any data allocated in the parent process is visible to the children. Okay, that's why this is called a shared memory paradigm, OpenMP. Okay, you can do a very fancy thing where you can launch MPI processes, and within an MPI process, you can spawn children and then merge them back and go back to the MPI process. That is called a hybrid MPI OpenMP programming. As for an example, if you want to see, you can go into systems, and that whole code that we were running for visualizing the pinning of processes. This is an example of a hybrid MPI OpenMP process. So
Is there an advantage with that for like our kind of problem?
Okay, our kind of problem. So the thing is, our kind of problems are memory limited, right? At least in LP, the advection kernel and the collision kernel is memory limited. Now you can spawn 16 MPI processes like this to saturate the memory bandwidth for the data transfer and so on. But suppose now when the data is already in your cache, you want to, and suppose your collide was actually compute bound. Suppose your collide was actually compute bound. Then you can use the remaining idle cores. So basically 128 minus 16, whatever that number is. That many cores, you can use OpenMP on them to parallelly process the compute intensive data that is already in the cache. So then you will bring down the compute nature also. So essentially the paradigm which is most general is you launch as many MPI processes as there are memory channels. And then for each MPI process, you launch as many OpenMP threads internal to that process such that basically whatever the number of cores you skip. So if this is one MPI process in this group, then take the other eight of launch this group as 8 MPI thread, 8 OpenMP threads inside it. Similarly, one MPI process here and 8 OpenMP process inside it, and so on. So basically, you're negating the memory bandwidth limited portion here by doing the MPI, and then you're negating or improving the compute bound portion by doing core parallelization here. Again, it depends on
right now. I mean,
because right now your collide is not compute limited.
Okay.
It might look compute limited, but if you actually profile it, it's actually memory bandwidth limited.
Okay.
because it's doing a lot of cache hit, cache miss. Means if we vectorize the whole thing, it will become full streamlined memory bandwidth limit, because nothing will be, there will be no cache misses. So the vectorization works both ways. Vectorization is not just for compute, like increasing compute performance. It's also for ensuring that whatever data was fetched into cache remains in cache without escaping onto RAM again. It's like a, what do you say? It's like a prison that you make. Once data is in, cannot go out. No, not prison, Hotel California.
Samiti, can
Yeah.
you sometime tomorrow or something like briefly talk about profiling, man? Code profiling, if possible.
Profiling
Like either like I've just used Cray Profiler
okay.
sometime back, but just know it just throws out a graph and stuff.
Yes.
But yeah, I've not done like proper profiling apart from that. So if
See, what I would suggest is it's better if we first do profiling by hand, huh? Because if you start off with profiling, no profilers, it will become like a crutch.
okay,
So
get too used to it.
yeah, exactly. Then once you've dirtied your hands with the in-depth analysis of the code itself, then you can, once you're experienced enough, it's like, you hire people to do the job for you. Then you can
Yeah.
hire a profiler.
Okay. Okay.
Okay, so we can discuss, but I would say let's do the dirty work by ourselves first once.
Yeah, that matters. Yeah, cool.
So, any questions about MPI, this whole MPI business? See, okay, again, if you're confused, and you're too shy to talk to me about it, you can always go to, this is why I keep putting all these videos, because videos talk to you, you don't have to talk to them. Not here, sorry, HPC. There is a whole list of MPI videos. Okay, not whole list. These are good enough actually. There's a one video series and there are 2 articles. This will MPI tutorial is actually a very nice website. It's very nicely done. So if you go to any of the MPI tutorial, don't go to the Chinese one. Okay, there's nothing much in the first one. If you go to the next one, where is it? Send and receive, MPI send, MPI receive. It gives you examples of how to write a ping pong program where you keep sending data back and forth between 2 processes. It's a very simple program. Doesn't have to be as complicated as I made it to look like. I just made it that complicated because I wanted to break some, mental models. Then you have a ring program where basically you form processes sending, or it's like this thing, relay race, where you send data across processes like a ring, and it comes back to the first process. Chinese whispers, basically, like that. Chinese whisper doesn't come back to the person, no? It just distorts and goes off. Finished. Yeah. Or, yeah, like this is the blocking process communication. MPI send, MPI receive, and then there are dynamic receiving, blah, 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 all those things. And then you have, they don't discuss asynchronous non-blocking sense. Okay, good. So then for the blocking part, you can just go through these tutorials, and unblocking or asynchronous communication, I showed you already. So just as a goodbye gesture, you can now see what I do when I try to launch using, suppose 2 MPI processes, and 2 OpenMP threads, okay, or 3 OpenMP threads. So OpenMP num threads is 3, and I will launch MPI run n with 2. And do this. I compiled with mpage, but I'll run with until MPI because mpage and until MPI are API compatible, so you can interchange those 2. See what it did. So the rank, as you now understand, is the MPI rank, and the numbers here are the numbers of the rank which these threads were spawned as children of. So you can see that there are 3 threads, OpenMP threads, with the same rank 0, which basically means there's 3 threads have been spawned in rank 0, and 3 threads here have rank 1. Okay. But they seem to be scattered like pretty randomly. There is no sequence to them. So local thread ID means inside rank 3, what are the local thread IDs? 0, 1, 2, 0, 1, 2. And this is a global thread IDs. Okay. Now you can start playing around with different options and see how they affect you. So for example, suppose I want these two MPI processes to spawn on the first core of each of these two sockets. So this is one socket from the square bracket you can see, and this is one socket from the square bracket. So I want the first MPI process here and the second MPI process here. And suppose I want the ranks MPI threads to just be consecutive to the mother process. Okay. So what I'll do is I'll keep OMP num threads to be 3 because that's what we want. I'll just put OMP places is cores because I want to pin it to ports, not overlap with each other or something. Like otherwise, if you don't say specifically, no, it can end up piling on top of the same core itself and so on. So you'll see an X or something in this if there are multiple threads piled up on the same core in this visualization. So cores. Up bind, I will say close. Close basically means it will try to put all the MPI OpenMP threads very close to the mother process or close to each other. So it will just be sequential, like sequentially distributed across the mother process. So, and for MPI now, how do I ensure that MPI ranks are pinned here and here? Again, for that, you can go off to is it? Oh, HPC tips section, the code of the documentation. So go to HPC tips. You will see binding MPI processes and OpenMP threads. It will give you for each of the MPIs that you're trying to launch with, what are the different syntaxes? Because different MPI, MPICH MPI has a different syntax, Intel MPI has a different syntax, and so on. So we are currently running with Intel MPI. So we have to do all this business. Okay. So export IMPI pin domain is bind. Basically what this means is how many processes or how many cores do you want me to skip when distributing the MPI processes? Since this is process core 0 and this is core 64, I'll be basically I'll be skipping one full socket. So 64 cores I'll be skipping. So domain is 64. Or basically how much bigger domain is each MPI process worth. So I'll say my MPI process is worth this whole domain by itself. No other MPI process should encroach on its domain. So that is what domain means here. Then there is pin order is compact. This is like basically, otherwise if you're using multiple nodes, no, it will try to put one MPI process on one socket here, then go to the other node and put 64 cores to be the domain for the second one, then come back for the third MPI process here and so on. Compact means it will do it sequentially. And MPI pin cell, again, the same thing is if you don't say this, it is possible that some of the MPI processes will start piling on top of each other on the same core. So I'll pin, like the minimum unit is one core. Or basically you can see it like this, that a domain is worth 64 unit cells or 64 cores. That is the brilliant language syntax that Intel has chosen to go for their MPI. This doesn't make sense, but okay. Now we are done with MPI pinning here, OpenMP pinning here. Now we will run and see threads. See, beautiful, no? As you wish, exactly. So, course, first MPI rank, 3 threads are here. Second MPI rank is pinned to this, and 3 threads are here. Now you can play around with all these options. You can see the documentation on those and figure out what will give you the best performance by just remembering this diagram. That's all.
Hey, Samitip, I have a
yeah.
I have a question in the submit script, man.
Okay. Yeah.
So in the submit script, you give, yeah, can you just, open that? I just want.
Yeah.
So here's.
Your voice is breaking. Or is it, am I topping off? Like
that's 4 nodes, right? And 16 cores.
Akhilesh, hi. Akhilesh, your voice broke in the middle. Can you just repeat what you said?
Hear me now?
Can you just say once more? Yeah.
Yeah, you can hear me now?
Yeah.
So basically you're giving here 64 processors, but 16 per node, right? 16 processors are residing in each node.
Yes.
So 16 processors are actually sharing a memory, right?
Yes.
But still we're doing MPI across them.
Oh, okay. Yeah. Correct, totally. See, the thing is this. No, that's pure laziness, nothing else. The thing is,
Sorry?
that's pure laziness, nothing else. So basically, the thing is, I understand. If you're inside a node, why do you want to do MPI? You
Yeah.
can do OpenMP. Yeah, perfectly fine. It's just that because we like to parallelize across nodes, we thought let's write a single unified, like single MPI based code only.
Okay.
That's all.
Okay.
Ideally, yes. Actually, you know what? This Intel people came and confused us. They kept saying when we were designing that previous cluster that in all our new test cases, we are seeing that hybrid OpenMP MPI parallel cores don't scale well. We asked them, would you have data? They said, no, it's a feeling, gut feeling our engineers have. Now, then we were like, oh, okay, fine. Intel is Intel, so don't argue with them. But later on, we realized, okay, everyone is engineer only. Everyone is like, what do you say? Every engineer should be questioned or question themselves, and so.
Right.
So finally,
So basically you can do OpenMP, no? That's it, no? Then you can do.
yeah, you can do, yeah. Not an issue. Actually, we will start doing that because there are some cases where we are finding that doing MPI is making the number of intra-node communication so bottlenecked, it's not worth it. It's best to go into a shared memory paradigm inside a node.
Right, because it's not even required, right? In some
Yeah, it's not required. Yeah, it's just laziness. That's all. We thought if we are going to use only MPI, then make it a full MPI.
Right. Okay, got it. Cool. Yeah.
Okay, any questions? Any other questions that are there? So, so ideally, if you want the optimal pinning count of MPI plus OpenMP for Rudra, the ideal option is this. We'll launch with 16 because there are 16 memory channels. There are a total of 128 cores. So per memory channel is associated with 8 cores. So you will launch OpenMP threads on those 8 cores to parallelize the compute bound parts. So it will be 8. Your domain size here will be 8 because each MPI process will be in charge of 8 cores and spawn 8 threads across it. And you'll launch with 18. So this is what it will look like finally. As you can see, Intel does a very interesting job where it puts rank 2 first and rank 0 after a certain offset, which is a bit weird. There's a bug in the Intel MPI launch, this thing. That will be fixed as soon as we report this to them. I keep forgetting to report this to them. Ravi, can you just remind me next time? I'll take a screenshot also so that I don't forget. So this is how it works. This is the ideal configuration of running a very optimized code on Rudra. OpenMP plus MPI hybrid. Unless you run everything open. Achha, by the way, Akhilesh, yeah, this brings me to a good point. Actually, you know what? You won't be able to do this kind of a memory bandwidth bound portion taken care of by parallelized across memory channels and then core parallelized across. Well, you can. You basically then you have to do OpenMP inside OpenMP. So you launch 16 OpenMP threads for the memory bound parts, and then inside each compute bound kernel, you parallelize using 8 OpenMP subthreads inside each thread.
Okay. So OpenMP within, so two OpenMP.
Yeah.
Okay.
OpenMP
And within,
OpenMP.
and within nodes, between nodes, MPI.
Yeah. But the thing is, OpenMP inside OpenMP is a bit, I don't know. I've never done that actually.
Okay, I don't know.
Because I have heard of people doing it, but I have never done it, so I don't know.
No, this actually question I had some time back, but I was wondering why is it that they're doing intra node?
MPI intranode. Yeah, it's
intranode.
No,
Sort of
what I said.
redundant.
Yeah, exactly. No, so what I said holds true. It's out of laziness, nothing else.
Okay, cool. Yeah, that'll be interesting. Yeah, sometime. Yeah.
Okay, then I think I took 1 hour extra, 1 hour 10 minutes extra. I'll immediately stop presenting my screen. Now, okay, so people, can you please tell me what you want to? Is it okay to have the last session tomorrow? We'll be discussing the core library, and that's it. That should do it. So basically, we had 1 day extra. Instead of 3.5, we had 4.5 days.
What time tomorrow? 10 o'clock.
10 to 12.
Yeah,
Okay.
fine.
Yeah.
Because basically the thing is, code library is one of the main 3 components of this camp. If I leave without doing that, all the managers will come and hit me.
Managers also, employees also.
Yeah. Okay. Okay. Fine. So we'll meet at 10 then. Again.
Okay, tomorrow
Sure.
10 o'clock, no?
Yeah, tomorrow 10 is fine.
Okay. Fine. Take it.
Okay, sir.
Okay.
Thanks, man.
Thank
Thanks a
you.
lot.
Okay, bye.
Bye.
Thanks, Amity.
Yeah.